Welcome to today's session. In this video, we'll explore an interesting problem titled number 1080, Insufficient Nodes and Root to Leaf Paths. We'll break down the problem, analyze potential approaches, and discuss their respective complexities. Let's dive in and learn together. In this problem, you are tasked with pruning nodes from a binary tree based on a given condition. Specifically, you are provided the root of a binary tree and an integer called the limit. The goal is to ensure that every root-to-leaf path in the tree has a sum of its node values that is at least equal to the limit. Any node that does not satisfy this condition, meaning all paths through that node have a sum less than the limit, is considered insufficient and should be removed. A leaf node, by definition, is any node that does not have child nodes. The input consists of the root of the binary tree and the integer limit, and the output is the updated root of the pruned tree. This means that the tree is modified in place, and only the nodes that satisfy the condition remain. To better understand this problem, let's consider an example. Here, we are given a binary tree represented as an array 1, 2, -3, -5, null, 4, null, and the limit is -1. Visualizing the tree structure, the root node has a value of 1, with two children, 2 on the left and -3 on the right. The left child, 2, has a single child -5, while the right child, -3, has a single child 4. The root-to-leaf paths in this tree are 1-2-5 and 1-3-4. Calculating their sums, we find that the first path sums to -2, which is less than the limit of -1, while the second path sums to 2, which meets the condition. Because the subtree rooted at node 2 contributes only insufficient paths, it is pruned from the tree. The updated tree retains only the nodes that are part of valid paths. After pruning the tree based on the given limit, the updated structure is represented as 1, null, -3, null, 4. This means the tree now contains only the root node 1, its right child -3, and the right child of -3, which is 4. The entire left subtree, rooted at node 2, is removed because all its paths failed to meet the required limit. This demonstrates how nodes are selectively retained or removed based on the sums of their root-to-leaf paths relative to the provided limit. Now let's explore a more complex example. Here, the input tree is represented as 5, 4, 8, 11, null, 17, 4, 7, 1, null, null, 5, 3, and the limit is 22. Visualizing the tree, the root node is 5, with two children, 4 on the left and 8 on the right. The left subtree includes nodes like 11, 7, and 1, while the right subtree contains nodes such as 17, 4, 5, and 3. Calculating the root-to-leaf path sums, we find that paths like 5-4-11-7 and 5-8-17 have sums greater than or equal to the limit, so they remain intact. However, paths like 5-4-11-1 and 5-8-4-3 have sums less than the limit and are pruned. This results in an updated tree that retains only the valid subtrees. In another example, the input tree is 1, 2, -3, -5, null, -4, 0, with a limit of 1. Here, the root node is 1, with two children, 2 on the left and -3 on the right. The left subtree contains a single child, -5, while the right subtree includes nodes -4 and 0. Calculating the root-to-leaf path sums, we find that all paths 1-2-5, 1-3-4, and 1-3-0 have sums less than the limit of 1. Since no path satisfies the condition, the entire tree is pruned, leaving no nodes behind. The output for this case is an empty tree, represented as. This happens because all paths in the original tree were insufficient, meaning their sums were strictly less than the given limit. To summarize, the problem challenges us to carefully evaluate each root-to-leaf path and prune nodes that do not contribute to valid paths. The constraints of the problem ensure that the tree can have up to 5,000 nodes, with node values ranging from -10 to the power of 5 to 10 to the power of 5, and the limit varying between -10 to the power of 9 and 10 to the power of 9. Edge cases include handling empty trees, trees where all paths are valid, and trees where all paths are insufficient. Additionally, trees with mixed positive and negative values should be carefully considered to ensure accurate pruning. To tackle this problem, we first consider the brute force approach, which involves a recursive traversal of the tree without any optimizations. The intuition here is quite straightforward. We traverse all possible root-to-leaf paths, calculate the sum for each path, and prune subtrees where the path sum is less than the given limit. This can be achieved through a depth-first traversal. For each node, we calculate the sum of the current path, and when we reach a leaf node, we compare the total path sum to the limit. Nodes that do not contribute to any valid path are pruned bottom-up by returning none during the recursion. This approach has a time complexity of O(n), since we visit each node exactly once, and a space complexity of O(h), where h is the tree height, due to the recursion stack. However, the drawback is that it doesn't optimize pruning during traversal, which means we might perform unnecessary calculations on subtrees that ultimately turn out to be invalid. A more efficient strategy involves using an optimized depth-first search with post-order traversal. The key insight here is that post-order traversal allows us to process the children of a node before evaluating the node itself. This enables us to prune subtrees as we traverse upward, avoiding redundant computations on invalid paths. Specifically, if both subtrees of a node are pruned and the node itself doesn't meet the path sum requirement, we can prune the node immediately. This bottom-up evaluation ensures that we discard invalid paths as soon as they are identified, making the solution much more efficient. By leveraging this traversal method, we can avoid unnecessary operations and focus only on nodes that contribute to valid paths. To implement the optimized DFS strategy, we follow a few clear steps. First, we use a recursive DFS to traverse the tree in post-order. At each node, we compute the maximum path sum of its left and right subtrees. If the maximum path sum of a subtree is below the threshold, we prune it by setting the corresponding child pointer to none. Then, we check if the node itself contributes to a valid path. If it does not, we return none to prune it as well. Finally, we return the updated tree, or none if the root is pruned entirely. This approach has a time complexity of O(n), since each node is visited only once, and a space complexity of O(h), where h is the tree height, due to the recursion stack. The post-order traversal not only ensures efficiency but also keeps the logic simple and easy to follow, making the solution both clean and optimal. When comparing the brute force and optimized DFS approaches, both have the same theoretical time and space complexity in the worst case. However, in practice, the optimized DFS performs better because it avoids redundant checks by pruning invalid subtrees earlier in the recursion. Another possible approach is using a breadth-first search, or BFS, which involves level-order traversal with a queue to track path sums. While this could work, it requires additional space proportional to the maximum width of the tree, making it less space-efficient than DFS. An iterative version of DFS could also be considered, which eliminates the recursion stack but adds complexity to the code without significant performance benefits. Overall, the optimized DFS with post-order traversal strikes the right balance between clarity, performance, and space efficiency, making it the best choice for this problem. In this problem, we need to prune a binary tree such that any path from the root to a leaf is removed if the sum of the nodes in that path is less than a given threshold. Our approach involves traversing the tree, computing path sums, and removing subtrees that don't meet the threshold. To achieve this, we'll use recursion to perform a depth-first traversal. The recursive function, which we'll call pruneTree, takes two arguments, node, representing the current node, and currentSum, which tracks the cumulative sum along the path from the root to the current node. The first step of the recursion is to handle the base case. If the current node is null, this means there's no tree to process, so we simply return null. This forms the foundation of our recursive approach. Now, to process the tree, we begin by recursively traversing the left and right subtrees. For the left child, we call pruneTree, node.left, currentsum plus node.val, and for the right child, we use pruneTree, node.right, currentsum plus node.val. These recursive calls allow us to explore both subtrees while updating the cumulative sum along the current path. Once the left and right subtrees are processed, we update the node's left and right pointers with the results of these calls. After this, we evaluate whether the current node should be pruned. If the node is a leaf, meaning both its left and right children are null, and the cumulative path sum, including the current node's value, is less than the threshold, we prune the node by returning null. Otherwise, the node is retained, and we return it as part of the prune tree. Finally, the root node, after all recursive calls, becomes the result of the function and represents the prune tree. There are a few key concepts to keep in mind for this algorithm. First, we use a recursive post-order traversal, where the left and right subtrees are fully processed before making pruning decisions for the parent node. This ensures that we have all the necessary information about the child nodes before determining whether the parent should be pruned. Second, tracking the cumulative sum along the path allows us to efficiently evaluate each path against the threshold without recalculating sums repeatedly. The pruning criteria are straightforward. A node is pruned if it is a leaf and the sum of the path leading to it, including its own value, is less than the threshold. Finally, we need to handle edge cases carefully. If all paths in the tree fail to meet the threshold, the entire tree will be pruned, and the function should return null. Additionally, single-node trees must be evaluated correctly based on the threshold. To implement this algorithm, we rely on the binary tree structure, where each node has val, left, and right properties. Recursion is our primary tool for traversing the tree, as it allows us to explore paths and backtrack naturally using the function call stack. In terms of complexity, the algorithm has a time complexity of O(n), as each node is visited exactly once, and a constant amount of work is done per node. The space complexity depends on the height of the tree. For a balanced tree, the recursion stack will use O log n space. However, in the worst case, such as with a skewed tree, the space complexity becomes O(n). This makes the algorithm efficient for both traversal and pruning, even for large trees. Here, we start by defining a tree node class, which represents the structure of each node in the binary tree. Each node has a value, and pointers to its left and right children, which are initialized to none by default. Next, we define the solution class, which contains the sufficient subset method. This method is designed to prune nodes in the binary tree based on a given limit for root-to-leaf path sums. Inside this method, we define a helper function called DFS, which performs a depth-first traversal of the tree. The DFS function takes two parameters, the current node and the cumulative sum of node values along the current path. If the current node is none, meaning we've reached the end of a branch, we return none to indicate there's nothing to process. If the current node is a leaf node, we check whether the cumulative sum of the path, including the current node, meets the given limit. If it does, we keep the node, otherwise, we return none to prune it. For non-leaf nodes, we recursively process the left and right children, updating the subtree references based on the results of the recursive calls. Finally, if both the left and right subtrees are pruned away, we prune the current node as well by returning none. After defining the recursive DFS function, we initiate the depth-first search starting from the root of the tree, with an initial path sum of 0. This ensures that the cumulative sum is calculated correctly as we traverse down the tree. The result of the DFS call determines whether the root itself remains part of the pruned tree or if the entire tree is considered insufficient based on the given limit. By returning the result of DFS, we complete the sufficient subset method, providing a clean and efficient way to prune the tree to meet the required conditions. Here, we begin the Java implementation by defining the structure of a binary tree node using the treeNode class. Each node has a value, and pointers to its left and right child nodes. The class provides multiple constructors to handle different initialization scenarios, whether the node has no children, only a value, or both children. Below the treeNode class, we define the main method, sufficientSubset, which takes the root of the tree and a limit as inputs. This method calls a helper function named DFS to traverse the tree recursively. The helper function is designed to determine if nodes along the path meet the required sum threshold. At this point, we start the definition of the DFS function, which takes the current node, the accumulated sum along the path, and the limit as parameters. If the node is null, meaning we've reached the end of a branch, the function simply returns null to indicate there's nothing to process further in this direction. Now, the DFS function continues by updating the current path sum with the value of the current node. If the node is a leaf, meaning it has no left or right children, we check whether the accumulated sum meets or exceeds the limit. If it does, we retain the node, otherwise, we prune it by returning null. For non-leaf nodes, we recursively call DFS on both the left and right child nodes, updating them in the process. After processing the subtrees, we evaluate whether both children have been pruned. If they have, this node is also pruned by returning null. Otherwise, the node is retained, as it has at least one valid child contributing to a path that meets the sum requirement. This logic ensures that only sufficient paths are preserved in the final tree structure. Here, we start with a basic tree where no pruning is needed. The input tree has a root node with a value of 1, and it branches out into two subtrees. The left subtree contains nodes 2 and 4, while the right subtree contains nodes 3, 5, and 6. The limit for the path sum is given as 7. We begin at the root node with an initial current underscore sum of 0. Adding the value of the root node, we update current underscore sum to 1. Then, we traverse to the left child of the root, which is node 2. Here, current underscore sum becomes 3 after adding the value of node 2. Moving further down to node 4, which is a leaf node, we update current underscore sum to 7. Since this value meets the limit of 7, node 4 is retained in the tree. After processing node 4, we return to node 2. Since node 2 has no right child and node 4 is valid, we keep node 2 in the tree. Next, we move to the right child of the root, node 3. The current underscore sum is updated to 4 after adding the value of node 3. From there, we explore its left child, node 5, where current underscore sum is updated to 9. Since node 5 is a leaf node and its path sum exceeds the limit, it is kept. Similarly, for the right child of node 3, node 6, the current underscore sum becomes 10. This also exceeds the limit, so node 6 is retained. With both children of node 3 being valid, node 3 itself is kept. Finally, the root node, 1, is kept because both its left and right subtrees are valid. The output tree remains unchanged, as no nodes were pruned. Now, we examine a tree where pruning is required. The input tree starts with a root node of value 5, branching into two subtrees. The left subtree contains nodes 4, 11, 7, and 1, while the right subtree contains nodes 8, 13, and 4. The limit for the path sum is 22. Starting at the root, we initialize current underscore sum to 0 and update it to 5 after adding the root's value. Then, we traverse to the left child, node 4, where the current underscore sum becomes 9. From here, we continue down the left subtree. At node 11, the current underscore sum increases to 20. Moving to its left child, node 7, the current underscore sum becomes 27. Since node 7 is a leaf node and its path sum meets the limit, it is retained. For the right child of node 11, node 1, the current underscore sum is updated to 21. However, this does not meet the limit, so node 1 is pruned. With one valid child, node 7, node 11 is kept. This makes node 4 valid as well, since its left subtree contains valid nodes. Now, we inspect the right subtree of the root, starting with node 8. Here, current underscore sum is updated to 13. For the left child of node 8, node 13, the current underscore sum becomes 26. As this exceeds the limit, node 13 is kept. For the right child of node 8, another node with value 4, the current underscore sum is 17, which is below the limit, so this node is pruned. Since node 8 has one valid child, node 13, it is retained. Finally, the root node, 5, is kept because both its left and right subtrees contain valid nodes. The resulting output tree includes nodes 5, 4, 8, 11, 7, and 13, with the pruned nodes removed. This illustrates how the algorithm effectively removes insufficient nodes while preserving valid paths. In this example, the input tree has a root node of value 1, branching into two subtrees with nodes 2 and 3. The limit for the path sum is 10. Starting at the root, the current underscore sum is updated to 1. Moving to the left child, node 2, the current underscore sum becomes 3. Since node 2 is a leaf node and its path sum is below the limit, it is pruned. Similarly, for the right child, node 3, the current underscore sum becomes 4. As this also does not meet the limit, node 3 is pruned. With both children pruned, the root node is also pruned. The output tree is empty, showing that the entire tree can be removed when no path meets the limit. The time complexity of this algorithm is O(n), where n represents the number of nodes in the binary tree. This is because the algorithm executes a depth-first search, or DFS, which visits each node exactly once. At each node, a constant amount of work is performed, such as adding the node's value to the current sum, determining if the node is a leaf, and potentially pruning the node if necessary. During the traversal, the algorithm also processes the left and right subtrees recursively, ensuring that every node in the tree is visited. As a result, the total computational effort is directly proportional to the number of nodes in the tree. Even in the best-case scenario, where nodes are pruned early, such as when the root itself is insufficient, the algorithm still visits each node once before making any pruning decisions. Similarly, in the worst case, where no nodes are pruned and the entire tree is traversed, the complexity remains O(n). This consistency demonstrates that the time complexity of the algorithm is robust regardless of the structure of the tree. Now, looking at the space complexity, it is O(h), where h is the height of the binary tree. This arises from the memory used by the recursion stack during a depth-first traversal. Specifically, each recursive call corresponds to a node along the current path from the root to a leaf, and the maximum depth of these calls is determined by the height of the tree. If the binary tree is balanced, the height is approximately log n, leading to a space complexity of O log n. On the other hand, if the tree is skewed, where nodes form a single straight path, the height equals the total number of nodes, n, resulting in a space complexity of O(n). Aside from the recursion stack, the algorithm uses only a small number of auxiliary variables, such as the current_sum, which occupy constant space, or O(1). Therefore, the overall space complexity is dominated by the recursion stack, meaning it scales with the height of the tree, O(h). To compare, a naive approach to solving this problem would involve explicitly generating all root-to-leaf paths and then checking the sum of each path against the given limit. This approach is highly inefficient because the number of potential paths in a binary tree grows exponentially with its height. Specifically, in the worst case, a binary tree of height h could have up to 2 to the power of h root-to-leaf paths, leading to a time complexity of O(2 to the power of h). Additionally, the space complexity for this naive approach would be O(h plus p), where h accounts for the recursion stack and p represents the memory required to store the paths. In contrast, the optimized DFS algorithm we're analyzing avoids the need to explicitly generate paths. Instead, it evaluates nodes in place, determining whether they should be pruned as part of the traversal. This reduces the time complexity to O(n) and the space complexity to O(h), making it much more efficient. Finally, let's formalize the time and space complexity using a mathematical proof. For time complexity, recall that each node in the binary tree is visited exactly once during the DFS traversal. With n nodes in the tree, this means the total number of visits is n. Since each visit involves a constant amount of work, the total time complexity becomes O(n). For space complexity, consider the depth of the recursion stack. This is directly proportional to the height of the tree, h. In the worst case, where the tree is completely skewed, the height equals the number of nodes, n, resulting in O(n) space. In the best case, where the tree is perfectly balanced, the height is log n, leading to O log n space. Thus, we can confidently conclude that the space complexity is O(h), where h represents the tree height, capturing both the best and worst cases. Here are some common mistakes to watch out for when solving this problem. First, not accounting for negative values in the tree is a frequent issue. Assuming all node values are positive can lead to prematurely pruning subtrees, even though negative contributions might still allow a valid path to meet the condition later. Next, an incorrect base case in recursion is another common pitfall. If you forget to check whether the current node is a leaf before calculating the path sum, you risk runtime errors or incorrect results, especially when dealing with null nodes. Another mistake is failing to reset state during DFS backtracking. For example, using shared variables for path sums without properly resetting them can cause sums from one path to unintentionally affect others. Finally, ignoring edge cases is a big risk. Scenarios like an empty tree, a single-node tree, or cases where all paths fall short of the limit should be explicitly handled, as failing to do so can lead to unexpected crashes or incorrect outputs. Inefficient pruning logic is another area where developers run into trouble. Checking the sum at every node instead of waiting until you reach a leaf adds unnecessary computational overhead without improving accuracy. Now, let's consider some interview insights to strengthen your approach. A key observation is that this problem often boils down to recursive tree traversal techniques like DFS or BFS. To solve it effectively, you need to understand when and how to prune subtrees. Optimizing early by identifying non-viable paths can save significant computation, as you avoid exploring unnecessary branches. Interviewers also appreciate when you proactively discuss edge cases, such as handling negative values, single-node trees, or even empty trees. Additionally, be prepared to explain the time and space complexity of your solution. For instance, a DFS-based approach typically has a time complexity of O(n), where n is the number of nodes, while the space complexity is proportional to the tree height, or O(h), due to the recursive call stack. This problem is also closely related to other tree-based challenges. For example, in the path sum problem, LeetCode 112, you check whether a root-to-leaf path matches a given sum. Path sum 2, LeetCode 113, takes it a step further by finding all such paths. Then there's path sum 3, LeetCode 437, where you count the total number of paths that equal a target value, and maximum path sum, LeetCode 124, which focuses on finding the maximum sum across any path in a binary tree. Now, let's explore alternative approaches. Iterative DFS or BFS can be used instead of recursion. This avoids consuming stack space from recursive calls, although it requires manual stack or queue management. It's particularly useful for very deep trees, where recursion might lead to stack overflow. Another option is memoization for path sums. While this can reduce time complexity by avoiding redundant calculations for overlapping subproblems, it comes with increased space usage. This strategy is especially helpful in trees with many duplicate subtrees or overlapping paths. Finally, you can use post-order traversal as an alternative approach for pruning. This method processes subtrees before making any pruning decisions, ensuring that you have complete information about a subtree before deciding whether to keep or remove it. However, a trade-off with this approach is that pruning decisions may be delayed, which could be less efficient in some scenarios. This traversal is particularly suited for problems where the pruning explicitly depends on analyzing entire subtrees first, aligning well with the requirements of this challenge. Thank you for joining me today. To summarize, we explored different approaches to solve problem number 1080, emphasizing recursion and optimization techniques. Key takeaways include the importance of recursive problem solving and understanding constraints to refine your solutions. If you enjoyed this session, do like, share, and subscribe for more coding tutorials. Keep coding and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!